So before we dive deep into the data products, first let's take like one step back to see like what's the overview data infra at the Airbnb. So as you can see there, the data infra is built based on the batch processing systems. There's two major incoming data sources. One is the analytics events coming from the web servers and all kinds of services. The other is the MySQL daily dump. We basically generate a MySQL snapshot and restore them in the warehouse on a daily basis. So these two major data sources batch ingest into the warehouse. We have two major warehouse. We call it gold and silver. So gold is try to run like a high SLA, like critical jobs, and silver is for like ad hoc purpose. People run ad hoc pipelines on top of this silver cluster. These two clusters actually in a different availability zone. So they also serve for disaster recovery purpose. We built a framework called Air to replicate the data, the Hive data from the gold cluster to silver cluster. So for the critical data set, it will be on both gold and the silver cluster. We also have two major computation cluster, Presto cluster and Spark. So these are dedicated like computation machine just for running Spark and Presto. We're using Airflow to schedule these batch pipelines. So user can define all this dependency and a DAG-like computation flow in Airflow. We also build a data visualization tool called Superset. So user can using more like a user-friendly interface to slice dice the query and run ad hoc query. So the Air, Airflow, and the Superset are all open sourced. And Airflow right now is a patch project. So last year, actually, we started new initiatives to onboard streaming processing at Airbnb. So we leverage Kafka to ingest the data and leverage Spark streaming to process like a different computation and write to different things. Like we write to Datadog for monitoring and alerting. We write to DynamoDB for online serving, and we write to Elasticsearch for online indexing. So we often say building data products requires to building the Lambda architecture. So what is the Lambda architecture? So Lambda architecture is a data processing architecture to handle large scale of data by taking advantage of both streaming and the batch data. It attempts to balance the latency, throughput, and the fault tolerance by using the batch processing to get a comprehensive view of the offline data. And in the meanwhile, it tried to using the stream processing to get a view of the online data. And finally, these two views of data need to be merged before present to the end users. So the rise of the Lambda is try to mitigate the traditional MapReduce kind of batch processing. So since we have both the batch processing infra and the streaming infra we talked about before, so the next steps is try to unify them to build a Lambda architecture in-house for the data products purpose. So on the streaming side, we mainly using the Spark plus the Kafka plus Spark streaming. On the batch side, we're using Hive data and using Spark SQL or Hive SQL for the batch query. So we built a new frame called AirStream to leverage this streaming and the batch infra. So AirStream is trying to unify the streaming process, is try to unify the computation for both streaming and the process and the batch process. So user can define the computation by specify the Spark SQL query on both streaming side and the batch side. And finally, the result will be merged in HBase, so people can get a final merged view on top of HBase. So there's two foundations of AirStream. One is try to unify the streaming, processing, and the batch. The other is try to provide a shared global state store. And we will get into these two foundations one by one. So what do I mean by unified API for AirStream? Basically, user only need to write a declarative job configuration. So in the job configuration, you specify three parts. The source, which is like where the data coming from. They could be coming from a streaming source like Kafka or coming from like a batch source. The batch source could be a Hive table, partition, or even a result of like a Hive query. So in the computation layer, so when user can specify the UDFs or like a different SQL to represent the computation logic. So that computation logic can be applied on both, applied on both streaming data and batch data. And once after all the computation, user can write this data back to different sinks, and these sinks can also be shared in both streaming case and batch case. It also provides like a single driver execution mode for both streaming job and a batch job. In addition, like we also leverage HBase as a state store. So why we need a state store? There's a stateless and a stateful streaming processing. For stateful streaming processing, we often need to share the state across multiple jobs. That's actually is a major difference compared to like a Spark 2.0 when you do the unbounded computation. Like the job state may not need to be local for one job. Sometimes you want to share the state across multiple jobs. Like one streaming job want to output some state, the other streaming job could consume that from there. So that's a shared state across streaming job. The second purpose is we need to merge the result of both. We need to merge the result. Can you guys hear me? Yeah. Okay. Huh? No, actually. So I will come closer to the. So the second part is we need a place to merge the streaming result with the batch result. And the HBase actually is a perfect fit for this because it has a more efficient API for both streaming writes and batch writes. So when we want to load a data frame into HBase, we usually pre-shard the HBase table into a fixed number of regions. Then we partition the data frame based on the region key. So each partition in Spark actually corresponding to one HBase region. So during the streaming case, we can easily write to HBase using the multi-put API. Also, in that way, actually, it's limited number of connections in your Spark cluster. You don't need to create so many connections from each partition across all the HBase regions. So the region to partition mapping is like a simply one-to-one. Another benefit is when you're using the batch mode, like when you want to load a data frame from Hive into HBase. Often you don't want to write to HBase with like a large data set. It will slow down HBase. It's a lot of workload in HBase. You want to generate the H file directly in your Spark job and back upload these like H files into HBase directly. In that way, you can reduce the write load significantly in HBase and reducing the loading time. And I think the nice interface for supporting both streaming and the batch is a unique differentiate compared to other like a key value storage. So we often evaluate other key value storage for that purpose, and we couldn't find a nice way to do both streaming writes and batch writes in an efficient way. In addition, HBase also provide a nice API for different read queries. Like people can do multi-get query for random lookups. They can do sequential scan with some prefix scan and a time range. That's also tends to be very handy when you want to build a state store. So why HBase? So I think we all know what is HBase, and we covered most of parts. And one thing we didn't really talk about is the merge the view. So in HBase, each row key can have multiple versions. So that turns out to be very efficient when you want to merge the result from both streaming and batch. So think about that way, like a streaming case can write to some row keys, and the batch case can have the same row key with different versions. And based on the application logic, people can decide what's the version they can use. They can use the timestamp, they can use different semantics for the versioning, and they can decide which one actually wins. Is the streaming result will override the batch, or the batch will override streaming. So a lot of customized logic can be built there based on the multi-versions. So here's what I meant about how to merge the store. So during the streaming case, all the streaming job can update the same row key with different versions. As you can see here, R1 actually can have 3 different versions at three different values. And when the batch data ready, you will run a batch query, and the batch query can update the R1 with a different version and a different timestamp of different value. And when you want to query R1 to get the merge the view, that you can apply customize the merge logic to get the merge the view from the R1. We also leverage HBase to a lot of streaming computation. Like for example, like in Airbnb, you want to get like what's the unique viewer for a particular listing in the last maybe 30 days. So it's a long window computation. Like there's some algorithm you can get like approximate value, but it's hard to get the exact value with a time range. Like you want to get exactly value what's the unique viewer for the 30 days. So we leverage HBase to do this kind of streaming distinct count. So on one side, there's a streaming job can continuously update HBase with the prefix. In this case, the prefix could be listing ID plus the unique user ID. And the timestamp is actually the time when the viewer viewed the particular listing. So when you continuously update HBase with that, and when you want to get the unique count, you can get a prefix scan with a time range like 30 days. In that way, you can get exactly the how many different like a unique count on a particular listing with a long time window. Another very useful use case is we're using HBase to counting the moving average. Like for example, like we want to count what's the average review score for the last year. Like it's also a long window. Like you need to keep counting these things in a moving window fashion. So the way we use that, we're using HBaseCount API directly. So we keep track of the total number of review count and the review score. And in that way, actually, they can avoid all this like a client-side read, modify, write. So all these count actually semantics will be happening in HBase directly. So in order to get the moving average, we will get the start. We'll get a difference between the start of the window and the end of the window, like for a year. In that way, we can get a total review scores count in 1 year and total review count in 1 year. And by doing these two, we can get a moving average of the review score. So we really believe actually this pattern can be extended to other streaming processing, the long window streaming processing. So user can keep the state out of the streaming job and using the external distributed storage to keep the state for the computation. And also they can leverage the time range based query to get the result for the computation. So in-house, we actually have multiple HBase connectors. We're using like a Spark HBase connector, we're using Zeppelin, and these tends to be very handy when we want to model the data on top of HBase and query HBase directly. We also build a in-house like a presto-hbase connector. We actually leverage HBase to do the streaming ingestion. So all the events, like a Kafka events, will ingest into HBase continuously. And the people want to query this data in a real-time fashion. So we actually built the Presto HBase connector, so user can run ad-hoc query on top of HBase directly. And basically, it's keep the schema mapping and using the region server as a split. And we also plan to open source that particular connector on the GitHub. So in Hive, actually, we run more batch query on top of Hive. When the data ingested into HBase, people can run like using different like input format to run on top of HBase. So one thing turns out to be very handy is HBase can take a HDFS snapshot directly. And the snapshot is very useful when people want to get a consistent view of the data. For example, when we ingest the data into HBase, people want to see what's hourly snapshot, what's the data like in the hourly boundary or like a daily boundary, especially when we like ingest the database changes. And when we're reading from HBase, like if we keep querying HBase with this hourly boundary, it will like slow down HBase with all these requeries. So we basically take snapshot of HBase on like hourly basis. And when people run the snapshot input format by default, it will restore the snapshot from HBase into another location. And that actually happens on each query. That's really slowed down when people using the snapshot input format. So one thing we did is we optimized the snapshot input format by skip the restoration parts. So people can query the snapshot directly in HBase. There's no restoration needed. However, that actually brings some problem because then you have to manage all these snapshots like a life cycle by itself. Oh, and snapshot by itself. So we basically did like we ignore the restoration part and then make sure the snapshot won't delete the write-ahead log in the HBase. Otherwise, they were causing out the data loss because the snapshot input format will actually replay the log and is it working? So hello. So the snapshot input format actually will initiate the edge region in each MapReduce phase and try to reconstruct the edge region. If you don't change that code logic, and they will actually replay the real write-ahead log and delete the edge write-ahead log, then will causing your data loss. So that's the first optimization we did. Remove the restoration and make sure they don't delete the edge log. In that way, you can have the MapReduce to read the real a live snapshot in HBase instead of restore it. The restoration really take a long time actually. Actually, that's a counter the purpose of we do a snapshot. The reason we do a snapshot is we don't want a data copying when we take the snapshot. It's we take advantage of H file links, so people can get a zero data copy, a snapshot directly from HBase, and restore the snapshot actually counter that purpose because then you copy all the bytes again into another HDFS location. So that's the major part we did, and by doing that, actually they become very popular. So user can actually get hourly snapshot coming from HBase, and they can running all kinds of batch query, create a high view on top of create external table and a high view on top of this HBase snapshot and run all kinds of batch pipeline there. And because it's running on top of snapshot, I don't worry too much about whether they can bring down HBase or not, because they don't really scan HBase, they scan HDFS directly. So next, I can share a few use cases how we leverage the AirStream, the lambda architecture to build the data products at the Airbnb. So the first use case I can talk about how we generate the database snapshot in the warehouse, in a kind of real-time fashion. So at Airbnb, we're using the MySQL as the primary data storage. It's near to moving from the online database to the offline, the Hadoop with a lot of bytes. They also need to be a little bit more real-time basis, just a few minutes or a few hours delay, so people can get more real-time insights of the database. And it's also need to keep the transactional across all the tables, because sometimes there could be a transaction in the database land, but when export to Hive, you break that transaction, then a lot of pipeline logic could be break as well. And in the database land, they do this online schema change all the time, so the system need to handle all this schema change automatically. So the solution we did is originally we need to restore the snapshot of a MySQL into a different MySQL instance. We're using RDS, we're using Amazon a computation framework. So in the RDS land, you can restore another MySQL snapshot, and then we run the batch ingestion job to scoop the data from the MySQL instance to Hadoop. The restoration actually takes more than 20 hours for largest DB. It's really slow. So the pipeline actually is 1 day behind the real production data. This becomes a major problem. So we actually try to using the HBase to solving that problem. So we basically back up the MySQL bin log every 5 minutes and back up the bin log into the S3. Now we can basically apply the computation logic to extract the bin log, get all these DML and XVID events from the bin log and replay them on HBase row by row. So in HBase, you can basically maintain kind of a row level, we get a row level replica data, and HBase kind of read the replica of the MySQL data. We're using the bin log offset as the version in HBase, so it can keep the exactly transaction guarantee in the MySQL. And the way we dump the HBase to Hive, it can take just 1 hour to finish all the ETL job. So in that job, basically, the input is the bin log. They can do the log parser and generates different kind of events and apply these events into HBase. So traditionally, we have another version. We're actually using the Kafka to publish off these bin logs and consume there and apply them on HBase. The problem of using Kafka is actually you don't get the disaster recovery story. For example, when the Kafka is down, you may have only 3 days bin log there, and if they cannot recover, you actually lost all the data. And because there's a row level like a replication data. So if you lost one, you basically get inconsistent data in the HBase and as well as in Hive. So actually choose to use S3 to back up all the bin logs so we can replay as long as we want. And also the replay logic is item important so people can replay multiple times. And if there's a bug, you can easily fix and replay the same logic again. So why this actually fit into Lambda architecture? Because when you get the bin log, you only get the delta change in the database. You don't get the baseline. So in order to dump the MySQL data, like a HBase data into Hive to get a consistent view of the MySQL data, we need to get a baseline. So the baseline we seeded from previous partition of Hive or can read from MySQL directly. So the computation logic actually can be shared for this like a delta-based bin log replay versus like a batch-based MySQL, like a MySQL ingestion. So the other use case we talk about is how we ingested the data like in a real-time fashion and into HBase. So people can use in different query engine like Spark, Hive, and Presto to query HBase directly. So in the Spark, we're using the open source like a Spark HBase connector. Presto, we have the in-house like a connector, and the Hive people you can use in both the table input format like or the snapshot-based input format. And we also have the data portal, which is the superset. People can run all kinds of ad-hoc. This is supposed to be a GIF, but it's PDF. So people can actually type all these like SQL query in a real-time fashion against this real-time data. So people can get all these like interactive query very fast and in a nice fashion. So that's for the real-time ingestion. Yeah. So summary, like I think. So AirStream basically provides two kind of foundations. The first one is try to unify the batch processing with the streaming processing by leverage the Spark SQL, leverage the UDF Spark SQL, so people can apply the same computation logic for both streaming and the batch. So most importantly, actually, they're using the state store, like HBase as a state store, so it can merge the result of both streaming data and the batch data. Also, it can share the state across multiple streaming jobs. And the rich API of like read can support different long window computation queries. And the snapshot mechanism make people easier to get hourly consistent view of the data and run ad hoc and the batch analytics query on top of it. So with that, I think that concludes my talk. And thank you all for the time. And we can take a few questions. Oh, yeah, that's the kind of, yeah, I think the question is whether this like snapshot is in the open source or in the fork in HBase. Actually, the code base is not in HBase, it's in the Hive like HBase connector. So we actually plan to open source that part. Like that's a kind of like a Hive feature. So Hive has the HBase, Hive HBase connector part. In that part, every query you run on the snapshot input format, they need to restore the snapshot. So, but if you want to remove that logic, you have to handle the lifecycle of the snapshot. If you don't delete this snapshot, actually, number of H files will go like unbounded, right? Because you have all these links, and the number of H file will grow like infinitely. So it's kind of we definitely can open source it, but there's some risk and a limitation there for that solution. And it has to be as a whole package. If you're just using that part without deleting snapshot constantly with some reasonable retention, there'll be a risk for HBase. Yeah, but we definitely has a plan to open source all this optimization, including the Presto connector. Yeah, so actually that's a very good question. So the question is how to make the the snapshot input format to open the H region as a read-only mode without like deleting the write ahead log and things like that, right? Yeah. So the solution actually is still like in the table, like a snapshot table input format, they will initiate the H region object for each mapper, and then mapper so the H region by default will replay the H log and delete the H, like split the H log and delete it eventually, right? So what we did is we actually changed the class loader to load a customized H region in memory, which split like try to replay the H log, but we don't delete the initial like a final result. We don't also split the direction as the same HBase does, so you can avoid all these conflicts. So in that way, you still can get a consistent view in the MapReduce job, but you don't affect the existing HBase runtime. Yeah, so the question is whether it's a private bench. It's in part of the Hive HBase connector. That's something we can open source. Yeah. So it's not actually in the HBase code base. It's in the like the Hive HBase connector code base. So the question is whether we have the batch job overrides the streaming job. So actually, that's exactly the DB export this framework works. So because it's very hard to coordinate like when the streaming job runs and when the batch job runs, right? So usually the way we bootstrap this use case is we let the streaming job run first. So you have the streaming continuously replay the delta of the MySQL changes into HBase first. Then when they cross the date boundary, then you schedule another batch job to get all the results from the MySQL directly to HBase. So there could be overrides. So we always treat like in order to bootstrap this kind of lambda architecture, you always start the streaming first. Then you have a batch job to correct all the results at a particular time. Then after that time forward, you get all the consistent view and comprehensive view of the data. So actually we leverage this like a HBase like a multi-version feature to make this happen. It overrides, yeah. It will override. Basically, like think about that way. Like the streaming pipeline could be lossy. Sometimes you could actually have some bugs. Like the data in HBase for that row could be wrong in that case, and the batch job actually can correct that particular version of row.
On the other hand, like if a streaming job is ahead, and like if it has, say you have two rows, and you wrote new data for both rows, your batch data might like undo the new data for half of the part and not for the other.
Yeah, I think the philosophy is in the lambda architecture, the batch job always provide a comprehensive view to correct the data of the streaming view. So in your case, I think the streaming data can be an intermediate result and could be accurate up to some point, but the batch job can have a function to correct that data. Like in your case, they can have a more comprehensive representation of the business logic and the upload the HBase result. Yeah.
How many versions are you?
So it's a case by case. Like for example, in this like a DB export case, the version is unlimited. We're using the bin log position as a versioning there. Yeah. Okay. Yeah. Thank you all.